This is How to Math with Dr. Ian Lundholm. In today's episode, Taylor and Maclaurin series. If you haven't already, please go look at Three Blue, One Brown's video on Taylor series. It's a really well done video and has good, intuitive explanations and illustrations that will help you grasp some of the more technical stuff that we'll talk about in this PowerPoint. So if you haven't yet, I will not be offended if you pause this video, go watch the Three Blue, One Brown video. It's on our playlist for our class, and then come back to this one. Okay. So yeah, Taylor Maclaurin series and remainder estimates. Sure, it's an extension of the mean value theorem. We'll talk about that today. Okay. So first, what are we doing? Kind of reviewing from power series here. This looks like a power series. We are assuming that we can represent a given function as a power series. Okay, great. Yes, yes. Cool. And we did this in the last video. Sometimes we can determine what the coefficients of the power series can be. And yeah, so this is a power series centered on x equals a. So a is just an x value. Yeah, and if we were going to, so this is, yeah, we're treating this, like an infinite polynomial here, where if we were going to plug in a for x, and we'd be looking at f of a, what would happen is that everywhere where we plug in a here for x would make a bunch of zeros in this expansion. All those would be zeros. And what we'd be left with is C0. So yes, f of a equals C0. I remember where this is going now. So the function value would just be, yeah, f of a is C0. Now, remember that we can differentiate these convergent power series within the radius of convergence. So if we take what we had before and we take its derivative term by term, using the power rule a bunch of times, we get this. And we know that if we're going to plug in a and find f prime of a, again, all of these would turn into zeros. And we'd find that f prime of a is C1. And if we did that continually, continue to take derivatives and then substitute in x equals a to find, these different coefficients at all of the different degrees, we would find that, f double prime of a is 2c2, and then f triple prime of a is 3 times 2 times c3, or 3 factorial. You've seen this in the video already, that why the factorials show up is because we continue to take successive derivatives using the power rule. And so, in general, the nth derivative evaluated at a is n factorial times the coefficient that we want. And so, in order to solve for said coefficient, we just divide both sides by n factorial, and we get this. And so this is how we find the coefficients in the Taylor series that we're going to be looking at today. We take the nth derivative, we evaluate that nth derivative at a, and then divide it by n factorial based on successive applications of the power rule. Right. Anyways, here is our Taylor series definition, where we have all of those, nth derivatives divided by their factorial terms, and then we're expanding this around the value x equals a, so we see x minus a getting repeated and the various powers there. This is the Taylor series because this one goes out, to an unlimited amount of terms. And it's a way to start off with a function and create a series based on that function. We're just using, so we have a function, we have a point that we want to expand about. And what we're doing with the Taylor series is we're using information about the function's derivatives to create a series representation of that function. It's pretty cool. And Maclaurin is just the special name that we give to a Taylor series that is expanded around a equals 0. So that's just a special name, nothing too serious there. Cool. All right, example number 1. Find the Taylor series. Expansion of f of x is 1 over x about a equals 3, and determine, if anywhere, that the Taylor series converges to 1 over x. Okay, so we can determine those coefficients of the series using the expansion that we just talked about, using the successive derivatives to come up with these coefficients. And yes, the 0th derivative of a function is just the function itself, so that part's just 1 over x, and when you evaluate 1 over x at 3, you get 1/3. And so C0 is just 1/3 divided by 0 factorial, which is 1. So our first coefficient, C0, is just 1/3. The next one, we take the derivative of what we have. So we get, that derivative. We plug in 3, and then we divide by 1 factorial, which is also 1, to get negative 1/9. Moving on. Here are the next several, no, this is just the second derivative. Here we plug in a. Here we divide by 2 factorial to get 1/27. Take a derivative, plug in a, divide by 3 factorial, which is 6. Okay, and in general, the coefficients end up looking like this. And we actually have a geometric series going on with these coefficients. Right, you can see that there's this geometric series here. With the 1/3 and then negative 1/9. There's a negative 1/3, ratio between successive terms. You multiply by negative 1/3, multiply by negative 1/3, multiply by negative 1/3. And so we're going to be able to use the geometric series formula in order to show that this one, converges on a certain radius around x equals 3. And right now we're hoping to prove that this series actually does converge towards our original function 1 over x on a certain interval. Yeah, in this case, we use the fact that we have a geometric series, and as long as we keep this x minus 3 term in check, in that, we definitely want this to be, not getting too huge. So, we use this inequality to make sure that x isn't getting too crazy. And as long as x is in between 6 and 0, that keeps this part in between 3 and negative 3, which when, combined with this 3 on bottom, makes sure that the entire geometric series is, has an absolute value of less than 1 for each of its terms. That means it's going to, converge. All that good stuff. We're able to use this geometric series formula to show that, yes, indeed, this thing does converge to 1 over x on that specific interval from 0 to 6. Yes, and do realize that this was a special case. Not everything is going to have a power series that looks like a geometric series. So we're not going to be able to use this strategy always. It's just a good one to start off with. In general, we're actually going to be using Taylor's formula to see if we can find, a radius of convergence. But yeah, what this means is that, the entire series does converge to 1 over x on that interval. Okay. Yes, and this is making a point here that we can truncate a Taylor series. We can cut off, the tail of it and just take the first n terms and have what's called a Taylor polynomial. And that would be a good approximation of the function. So here are 4 examples of various order Taylor polynomials. And on the next slide, we'll see what those Taylor polynomials look like. These are the best first order, second order, third order approximations of our function 1 over x. So yeah. P0 is just a constant function. P1 is a linear function. P2 is quadratic. P3 is cubic. And you can see how they all start to, converge towards the actual function on that interval from 0 to 6 as the polynomial's degrees get larger. This is the formal definition of a Taylor polynomial, which is just a Taylor series with the tail cut off. So yeah, that should look pretty familiar. And again, the Maclaurin polynomial is just the Taylor polynomial where a equals 0. So you don't have to worry about subtracting the a off of all of these terms, which is, kind of nice to look at. Let's take a look at the Maclaurin polynomial for sine of x. And actually, I think already in the 3 blue 1 brown video made a very good, illustration of, I think he used cosine of x. But here sine of x, do know that, the derivatives of sine of x follow a nice cyclical pattern, where you'd have sine of x as the original function cosine as the derivative, negative sine as the derivative of cosine, negative cosine as the derivative of negative sine, and then back to sine for the next derivative. And so these things repeat every 4 terms, and that's how you get this crazy piecewise definition where, yes, you do have sines on the even terms and you have cosines on the odd terms, and the signs on those trig functions alternate depending on where you're at. So this is just a technical piecewise definition of how those derivatives behave. Specifically, we're looking at, what these functions are evaluated at 0 because we're doing the Maclaurin polynomial. All right. And when you plug in all of those various ones, zeros, and negative ones, you can see that for sine of x, we get the odd powers of x that survive. All the even powers of x had 0 coefficients, which is, not just convenient, but necessary. Since sine is an odd function, it makes a lot of sense that we have, it's built out of odd polynomial parts. Yeah. And so it's really just, the odd powers with odd factorials on the bottom. Cool. And there's just it written out in general. All of the terms that survive here look like that. These are just all the odd values. Yep. Yep. Okay. Great. And here we're describing the family of Maclaurin polynomials. This is harder than what it looks harder than what it is. What it's saying is that polynomials of odd order all look like this, where it's just the odd term, the odd terms, I guess, I don't know. You've got a bunch of odd numbers, odd degrees here in the Taylor polynomial. So we see a bunch of odd numbers, and then for an even polynomial that's trying to describe sine of x, it's just the odd numbered polynomial plus 0, basically, because all of those even terms have a coefficient of 0. And so the best approximation of sine of x when you're looking at an even derivative is the best. It's the best approximation is still the best odd polynomial that you've already looked at. That was explained better on the video on the 3 blue 1 brown video. But yes, this is the best odd power approximation. This is the best even power approximation. So the approximations don't get any better when you try to include the even power terms. It's just zeros. Okay, no big deal. Yes. So that's all that this is saying. both the fifth order and sixth order or Maclaurin polynomials are the same thing. Okay, and here's just a look at what all of those polynomial approximations of sine would look like. And they do get better and better as you increase the order of the polynomials. These ones go all the way out to the 22nd polynomial. So that's a polynomial with a degree of 22. And we're only out to, about, let's say 5 pi halves, you know, where it's a very good approximation. And then that starts to, diverge away from sine. But actually what we're going to, show at the end of this is that these Taylor polynomials do actually converge to sine of x for any x. The radius of convergence here is infinite. So this isn't going to stop converging at a certain radius like the last one we looked at. Okay, here we're going to take a look at when Taylor series converge to their generating functions. And so this is different than what we've done, previously for the power series. When we were looking at power series, we were really just concerned with, do those power series converge or diverge? This is taking it a step further, and we're going to be looking at not whether it converges or diverges, but does the Taylor series converge to the specific function that we want it to converge to? And yes, this thing is actually a generalization of the mean value theorem. Real quick, if you might remember the mean value theorem, where let's say this was our function f, and we were looking at f over an interval AB. The mean value theorem says that the average rate of change is playing an important role. It says that, the average rate of change, which would be f of b minus f of a all over b minus a. There's our average rate of change over that interval, would need to be equal to the derivative of this function evaluated at some point c. So we have a continuous function on this interval, and we're saying that there's some c in this interval where the derivative at c matches the slope of the average rate of change over the interval. So that's a very quick synopsis of the mean value theorem. And why does that apply to our new Taylor's theorem here? Well, that same c pops up here in the last, term. Here we have n continuous derivatives of f, and we know that, the n plus first derivative exists on this open interval AB. Here we're actually able to say that the function value evaluated at b, which is the the endpoint of this interval, is equal to this whole Taylor polynomial, really, because this is not a Taylor series. We do end at the n plus 1th term. But we're able to say that, yes, that the function evaluated at that endpoint is the same as this entire approximation over here. Or not approximation, really, because we find the special c value that makes the entire thing equal. And this is, it's very much like, it's just a rearrangement of the mean value theorem above. If I multiply both sides by b minus a, here, I'm going to do that real quick. Oh my goodness. I just want to show you that multiply both sides by b minus a, and you get f prime of c times b minus a. And then if you add f of a to both sides, you get the same thing here, right? It's just for, f of a plus f prime of c times b minus a. Okay. You get the same thing. It's just a first order, instance of this Taylor's theorem. And yeah, it should remind you of linearization. It should remind you of, the fact that we were able to, approximate what's going on here with a line. Right. So, that's Taylor's theorem. The important thing to notice is that we do have equality here. And this is not a Taylor series. It's just a Taylor polynomial. This thing actually ends. And so normally we'd think of Taylor polynomials being an approximation, but actually finding this special value c rather than just using a as the thing that we plug in everywhere, we actually find the special value c that makes it, instead of an approximation, it actually makes it equal. Let's keep going, because, I don't know, that's not, the technicalities of that aren't hugely important. Right. But the main thing is, what we're going to be able to do is tell whether or not a function actually converges towards its generating function based on the behavior of this last term. If this last term goes to 0, then we are golden. All right, Taylor's formula. Yeah, that looks like what we've looked at so far. Great. Oh, right. All this is really, I remember what all this is really reminding us to do is to point out the fact that we're going to be calling this whole portion P of n for the nth order Taylor polynomial. And we're going to call this one R sub n, which is the remainder for that Taylor polynomial. So the Taylor polynomial is the approximating part. And then this remainder term is the one that would get us to equality if we find the special value c. And really, just like the mean value theorem, all Taylor's theorem is saying is that c exists. It doesn't necessarily provide a way to actually find that c. And so it's, a bit of a mystery in a lot of cases. But if we can prove that this remainder term goes to 0 as n approaches infinity, then we're going to be able to prove that that our Taylor polynomials converge to the actual function that we want to converge to. So yeah, we've split up f of x into Taylor polynomial plus remainder term. Does this remind us to say anything important? Yeah, I mean, I guess this is just saying that we are definitely interested in when that remainder term goes to 0 as n goes to infinity. Because that's precisely when the Taylor series converges to the generating function. Okay, cool. So we're going to prove that e to the x does converge. The Taylor series, or yes, the Maclaurin series, because we're going to look at the Taylor series centered at a equals 0. Yes, that this Taylor series does indeed converge to e to the x over all of the real numbers. So the nice thing about e to the x is that all of its derivatives are just e to the x. And whenever you plug in our value of a, which is just 0, we always get 1. And so all of the coefficients on e to the x, goodness, go back. Come on. All right. All of the coefficients on, this polynomial are just, we've got 1 for the derivative and we're dividing by the factorial. So this is very nice, very simple in terms of a Taylor polynomial. Cool. And we've already seen that this thing as a power series is absolutely convergent. We used the ratio test on this, and we've shown that this is absolutely convergent. But we haven't shown that this thing converges towards the function e to the x. That's the piece that we've been missing so far. So here we're going to use the fact that we have shown that this thing converges before using the ratio test, which means that the limit of all of its terms do eventually go to 0. We know that, right? And we're going to break it down into 3 different cases based on whether we're looking at a negative number for x, whether we're looking at 0, or whether we're looking at a positive number for x. So here we're looking at a negative number for x. And the remainder on a nth order Taylor polynomial would look like this. Now, if x is less than 0, it means that, our n plus 1th derivative would be e to the c, and that e to the c would be less than 1, right? Because c is less than 0. So we get this nice inequality, and that allows us to make this inequality down here. We just substituted 1 for this whole piece. And we're left with this, and taking the limit as n goes to infinity here is just 0, based on the fact that we know that this one goes to 0. That's, yeah, the one for n. This is the same exact thing where we've got n plus 1. So here's where we've shown that this remainder term goes to 0 as n goes to infinity for x when x is a negative number. Here, we've got x is 0, and if x equals 0, then the remainder term just equals 0, and so that limit is just 0 as well. That's no big deal. And if x is positive, we have Taylor's formula again. This piece is still e to the c. And now this time we know that c is in between 0 and x, because remember, I mean, yeah, this is like the mean value theorem thing that we've done so far, but this time the endpoint out here is x. Instead of b, we're using x. And so the value c is somewhere in between 0 and x. And since we know that e is an increasing function, we know that e to the c is less than e to the x. And we're able to do, the same thing here. We're substituting in e to the x for e to the c and making this inequality happen. So that again, we get this limit that we know goes to 0, and we multiplied basically something that goes to 0 times e to the x. And, as n goes to infinity, this whole thing converges to 0. So again, we've shown that the remainder term goes to 0. And so for any value x, whether it be negative, 0, or positive, we've shown that our Taylor series converges to e to the x. Woohoo! Cool. And yeah, we'll often make use of this specific limit when we're showing Taylor series convergence. Cool. All right. So that one was about e to the x. Here we'll look at sine of x, which is very, very related to e to the x. This is a little bit of a teaser for the next lesson. Let me see if I can pull up e to the x here. You might notice that, e to the x has even-powered terms, and it also has odd-powered terms. And the odd-powered terms in e to the x are going to look an awful lot like the terms in sine of x. So here we have x cubed over 3 factorial. We have an x to the 5th over 5 factorial later. That's e to the x. Going back over here, for sine of x, remember that this one would look like x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. So the Taylor series of e to the x and sine of x are pretty similar, and we're going to see even more in depth the relationship in the next lesson. Anyways, we're trying to find when does this Taylor series actually converge towards the function sine of x. And again, what we can do is, look at the remainder term for the nth order Taylor polynomial and put some bounds on that. We know that the nth derivative, or the absolute value of the nth derivative, would be less than or equal to 1, just based on all of the derivatives of sine of x. And so we're able to make this inequality. And yes, this does go to 0 as well, just like in the last problem. And so, yeah, that's good. Um, yeah, no matter what x is, we converge. So again, this one converges everywhere. And this is just a little review. In example 1, we looked at the function f of x equals 1 over x, and we showed that that converges on this interval. We showed that e to the x and sine of x both converge everywhere, but this next example shows that not all Taylor series are that well behaved. This next one is only going to converge at a single point. Here we have the function f of x equals, e to the 1 over x squared, or negative 1 over x squared. This function is kind of funny looking. I'm going to just scroll over to what it looks like real quick. It is very, very flat around x equals 0. And so when you take successive derivatives of this thing, you keep getting 0. You have to do a little bit of work. Here they're using L'Hopital's rule to show that the derivatives are in fact 0. But this is a function that when you try to find its higher order derivatives, you always get 0 back when you're, centering it at x equals 0. And so the Taylor polynomial that you get is, very, very boring, or the Maclaurin series, because we're centered at 0, is just adding up 0 a bunch of times. And so, this one only converges at that one point. It's not very useful. Which is, I don't know, it's just a cool example of a case where it's not necessarily Taylor's theorem is wrong or contradicted by this function, but since the function is just extremely flat at that point, the derivative information is not giving you useful information, and therefore you're not able to make a useful Taylor polynomial based on that derivative information. I bet if you moved over here and said, let's make a equal 1.5, and you tried to start making a Taylor polynomial over here, then I bet over there things would be much nicer, and you could make approximations. But here things are bad. Okay. Maclaurin series expansion of cosine of x. We've already done sine of x, and we could make the expansion of cosine of x based on first principles, but what about if we just take the derivative of sine of x? So here we look at the Taylor series of sine of x. We differentiate it term by term, and we get this. Ooh. This one actually, it's a lot of gobbledygook to look through. But, this one ends up being, 1 plus, or it's minus, shoot. Nope. Daggone it. Eraser. There we go. 1 minus x squared over 2 plus x squared over 4 factorial minus so on and so forth. It's a bunch of even powered terms. As you can see, yeah, we've got even numbers on top, even numbers on bottom. And you can see, again, this one's very similar to sine. It's very similar to e to the x. In the next lesson, we're going to see how they combine together. Cool. So you can find other Taylor series based on ones that you already know by differentiating. On this one, we already know e to the x. And so what would happen if we, instead of trying to come up with a Maclaurin series for this from scratch, what if we use the fact that we already know the Maclaurin series for e to the x, and we just plug in negative x squared in everywhere where we see x in the expansion down here. So we literally just plug this piece in to the normal e to the x Taylor series, Maclaurin series. And yeah, we get this guy. So that's, I mean, this is just showing another way that we can build off of what we already know and create new Maclaurin series based on what we already know. That was a pretty easy way to make a Maclaurin series. Here we have this function, e to the negative x squared. Remember that this is a non-elementary integral. Earlier on this semester, we used a little bit of numerical analysis, numerical integration to solve this one, whether it would be, just doing a Riemann sum or using the trapezoidal or Simpson's rule. We've talked about how to deal with non-elementary integrals before, but this time we're going to be able to use the Taylor series, the Maclaurin series that we formed for this, and recognize that this thing is an alternating series, right? To give a really nice approximation within 1/1000th. Yeah. So this is what the first 5 terms look like. And since it's an alternating series, we know that we can stop there because we're within 1/1000th. The next term is 1 over 1,320. So yeah, we're within 1/1000th of the actual answer just by looking at the first 5 terms of that Taylor series. That's pretty cool. That was a very fast way to determine a good approximation for that non-elementary integral. Okay, moving on. I know you guys are starting to get tired. I'm starting to get tired. Find the Taylor series expansion of ln of x around a equals 1. Cool. So how does ln of x relate to anything that we've looked so far? Ln of x is the antiderivative of 1 over x. And so what we're going to be able to do is take the Taylor series for 1 over x that we've already looked at. Remember, this is the Taylor series for 1 over x, which we built based on the geometric series formula. And we're going to be able to take this Taylor series, take its antiderivative, so we're going to add 1 to the power and divide by that power over here. to get a Taylor series for the natural log of x. Yeah, do remember that this Taylor series only converges for x's that are, close enough to 1, within a radius of 1, so from 2 to 0. This will also maintain that same radius of convergence. And now the interval convergence actually includes the endpoint x equals 2. But yeah, we actually just found that Taylor series by integrating. Cool. And know that sometimes you'll see at the ln of x Taylor series written this way. Sometimes you will see it written this way just based on the index that you have here at the end. But ln of x is one of those that, is fairly common. Oh my goodness. Okay. And for example number 10, if we wanted to find these series where you just multiply by x, literally you can just multiply by x the series that we've seen so far. So for sine of x, literally if you multiply by x here, which, is that you get a new series. Woohoo! And this one again, a lot of gobbledygook, but yes, multiplying through by x, there's definitely some, algebra being done here, but this is just a fancy way to write x so that things reduce nicely in the end. Nothing too major there. This table is not necessarily something, especially in this context, where you're going to have to memorize these Taylor series, but do realize that there's a version of this table in your book. I forgot to look up the page number, exactly where this is, but it's at the end of this chapter, or the end of this section. But yeah, here's just some common Taylor series. And in the next one, we are going to look at how e to the x and sine of x and cosine of x are all related. So I'm excited for that. Yeah, those are just some common ones. Thank you for continuing to participate in our class. We are getting very, very close to the end. This was section 10.8. We will have section 10.9 next Monday. And then that will be our last piece of new material for the semester. So that's exciting. All right. I hope you have a great day. Have a good weekend. Please let me know if you have any questions as you are watching this or looking through your online homework. All right, guys. I'll talk to you later. Bye.